2.6.5 Homogeneous spacetimes. Action of a Lie group. A Lie group G acts on itself by left multiplication and by right multiplication. There are similarly two ways that G can act on any manifold M. Definition. A left action of a Lie group G on a manifold M assigns to each A is a member of G a diffco A, MM satisfying. See the equation. All A, B is a member of G, P is a member of M. Definition. A right action of a Lie group G on a manifold M assigns to each A is a member of G a diffio A, MM satisfying. See the next equation. All A, B is a member of G, P is a member of M. An action of G on M is transitive if every point of M can be reached from any other point of M by the action of an element of G.
See the equation shown. Written for a right action. An action is simply transitive if every element of G except E moves every element of M. PA equals P right double arrow equals E. If G acts simply transitively on M, then, as a manifold, G is diffeomorphic to M. Proof: pick a point P in M. Define a diffeo psi sub P colon G goes to M by psi sub P of A equals PA map is onto because the action is transitive. It is 1-to-1 because the action is simply transitive. Note that the arbitrariness in the diffeo lies in choosing what point P to assign to the identity E of G. Once one has chosen an origin, P, the rest of the diffeo is determined by the group action.
Theorem: a simply transitive action of a Lie group G on a manifold M maps the Lie algebra German G of G to an isomorphic Lie algebra of vector fields on M. In fact, given a vector field xi to the A power in German G, each diffeo psi sub P drags xi to the A power to the same vector field xi to the A power on M, independent of the choice of origin P. Proof: we have shown previously that diffeos commute with Lie derivatives. Let xi bar to the A power equals psi sub P times A to the alpha power xi to the A power. See the equation. We must show that xi bar to the A power is independent of the choice of diffeo psi sub P. Let G of lambda be the one-parameter subgroup generated by xi to the A power. Then at a point Q equals PA, xi bar to the A power is tangent to P of A G of lambda, equals P of A times G of lambda equals Q G of lambda. In the final expression, P does not appear. The curve lambda goes to Q G of lambda is independent of P, so its tangent, xi bar to the A power is independent of P.
Spacetimes foliated by with homogeneous space-like slices. Let M with G sub alpha beta be a spacetime on which a group G acts on the right and for which each A is a member of G corresponds to an isometry of M. Each diffeo A. .mm leaves the metric of M invariant. Homogeneous universes are, in addition, foliated by a family sum from T to of space-like hypersurfaces on each of which G acts simply transitively. Then each point of a slice sum from T to is identical to every other point of a slice. Homogeneous does not imply isotropic. A uniform magnetic field and a macroscopic crystal are homogeneous but not isotropic. In a homogeneous but anisotropic gravitational field, for example, tidal forces are direction dependent. The transitive slices of a homogeneous spacetime are orthogonal to a family of timelike geodesics. The proof uses the fact that the component of momentum along the killing vector is conserved by a free particle.
Theorem: let U to the alpha power be tangent to a geodesic gamma of lambda with affine parameter lambda, and let xi to the A power be a killing vector. Then U sub alpha xi to the A power is constant along gamma. Proof: d over d lambda times U sub alpha xi to the A power equals U to the beta power gradient sub beta, U sub alpha xi to the A power equals U to the alpha power U to the beta power gradient sub beta xi sub alpha plus xi sub alpha U to the beta power gradient sub beta U sub alpha equals 0. See equation 2-100. Where each term vanishes separately, the first by Killing's equation gradient sub beta xi sub alpha antisymmetric, the second by the geodesic equation U to the beta power gradient sub beta U to the alpha power equals 0. For a timelike geodesic, P sub alpha xi to the A power is a conserved component of the 4 momentum P to the alpha power equals mu to the alpha power.
Consider the family of geodesics to a homogeneous hypersurface sum from 0 to, with unit T to the alpha power. We want to show that each geodesic gamma in the family is to every hypersurface sum from T to. The images xi to the alpha power of the vectors in the Lie algebra of G span the three-dimensional tangent space of sum from T to at each point of sum from T to. Hence gamma is to sum from t to if, and only if its tangent t to the alpha power is to each vector xi to the alpha power. But by construction, on sum from 0 to t sub alpha xi to the alpha power equals 0, and by the theorem, t sub alpha xi to the alpha power equals 0 is conserved along gamma, so t sub alpha xi to the alpha power equals 0 on sum from t to. If we choose the parameter t to be proper time along each geodesic gamma, then t sub alpha equals negative gradient sub alpha t. The sign makes t to the alpha power future pointing, t to the alpha power gradient sub alpha t equals 1.
We can write the metric in a simple form in terms of a basis of 1 forms w to the mu power with w to the 0 equals gradient sub alpha t, and with w to the I power the image on each sum from t2 of a right invariant basis on G. Unlike the left invariant vector fields that generate the right action of G, these right invariant forms depend on the choice of diffeo psi sub p. One must pick a basis, w to the I power orthogonal to w to the 0, at a point p of sum from 0 to, and extend the basis to every pomp q of sum from 0 to by the diffeos a. That is, the I power of w of q equals the star power of a of the I power of w of p. See equation 2-101, where q equals pa. Finally, extend w to the I power to all of m by requiring that script L sub t w to the I power equals 0, or, equivalently, the I power of w of t equals phi sub t the I power of w of 0, where the set phi sub t is the family of diffeos generated by t to the alpha power. Because the Lie algebras of left and right invariant vector fields of a group are isomorphic, we have the relation.
See equation 2-102. Where c sub j k to the I power are the structure constants of the Lie algebra corresponding to the basis omega to the I power. Abstractly, the images xi eta under psi sub p of right invariant vector fields on G satisfy. See equation 2-103. Where c sub beta gamma to the alpha power is the image of the right invariant structure constant tensor on G, and we can write. See equation 2-104. By construction, the basis omega to the mu power is invariant under the action of G. Because the metric G sub alpha beta is invariant under G, its components along omega to the mu power are constants on each sum from t to. We have. See equation 2-105. Because the metric components depend only on t, and the structure constants c sub jk to the I power are constants, the Einstein equations are now a set of ordinary differential equations, easily solved by computer.
Bianchi's classification of three-dimensional Lie groups, with only one exception, SO of 3 times R, acting on S squared times R. Every group that acts transitively on a 3-manifold sum from to has a subgroup that acts simply transitively on sum from 2. When the action is simply transitive, sum from 2 is a copy of G, so one can classify homogeneous spaces by classifying the three-dimensional Lie groups. Ignoring the global topology of the space, this is equivalent to classifying the three-dimensional Lie algebras. The classification is due to Bianchi, first applied to homogeneous spacetimes by Taub and Math. 53, 472-90, 1951.
We want to classify the possible structure constant tensors C sub bc to the 8 power of a three-dimensional Lie group G. First note that an isomorphism psi colon G goes to G maps C sub bc to the 8 power to the new structure constant tensor, psi sub d to the 8 power psi sub b raised to the negative 1 e power psi sub c raised to the negative 1 f power c sub ef to the d power. Any invertible linear transformation psi sub b to the 8 power can be obtained in this way from some isomorphism in this way. Because we want to regard as identical two Lie groups that are related by a diffeo, we need to find the classes of tensors C sub bc to the 8 power invariant under similarity transformations, or, from a passive viewpoint, we want classes of structure constants C sub jk to the I power invariant under a change of basis.
What does it mean to find invariant classes of tensors? For a vector a to the alpha power, there are only two classes, the class consisting of the vector 0, and the class consisting of all non-zero vectors. Given any two non-zero vectors, a to the alpha power, b to the alpha power, there is always an invertible linear map that takes a to the alpha power to b to the alpha power. In 3 dimensions, any non-zero antisymmetric tensor a raised to the ab power is similarly equivalent to any other antisymmetric tensor. Pick a metric xi raised to the AB power and a corresponding totally antisymmetric tensor epsilon sub ABC. The nonalization, 1/2 epsilon sub ACD epsilon sub B raised to the CD power equals delta sub AB, fixes epsilon sub ABC up to an overall sign. Then one can uniquely associate each antisymmetric tensor with a vector by taking the dual.
See equation 2-106. And the operation is invertible. See equation 2-107. It is, of course, this duality relation for tensors on R³ that allows one to replace the wedge product, U wedge V, of two vectors by the cross product, U times V equals sub raised to the star times U and V. Then a Lie transformation that takes sub raised to the star A to the A power to sub raised to the star B to the A power also takes a raised to the AB power to be raised to the AB power.
Finally, symmetric tensors, M raised to the AB power, are classified by their rank and signature. The rank of M is the number of non-zero eigenvalues, the dimension of the space of vectors for which M raised to the AB power V sub B is not equal to 0. One can always diagonalize a symmetric tensor, i.e., write a symmetric matrix M raised to the AB power of rank n in terms of n orthogonal normalized eigenvectors U, V M raised to the AB power equals plus or minus U to the A power U to the B power plus or minus plus or minus V to the A power V to the B power. Any two tensors M prime with the same number of non-zero eigenvectors and the same signature, set of signs, are equivalent because there is a similarity transformation that maps U goes to U prime, V goes to V prime. Tensors M raised to the AB power with the same rank but different signatures cannot be in the same invariance class, because a similarity transformation maps M raised to the AB power goes to M raised to the prime AB power equals plus or minus U raised to the prime A power U raised to the prime B power plus or minus V raised to the prime A power V raised to the prime B power, thereby maintaining the set of signs.
The Bianchi classification proceeds as follows. The tensor C sub BC to the A power antisymmetric on B, C, is equivalent to its dual. See equation 2-108. Write *C as the sum of its symmetric and antisymmetric parts, let. See equation 2-109. Then, see equation 2-110. And A is the trace of C. See equation 2-111.
Finally, C can be expressed in terms of A and M. See equation 2-112. A Lie algebra is determined by a structure constant tensor satisfying the Jacobi identity. See equation 2-113. This turns out to be simply the relation. See equation 2-114. Conclusion. A three-dimensional Lie algebra is specified by a symmetric tensor M raised to the AB power and a vector A to the A power satisfying M raised to the AB power A sub B equals 0. The three-dimensional Lie algebras are, thus, classified by the rank and signature of M raised to the AB power and by whether or not A to the A power is 0. Bianchi type A to the A power classification of MI 00020 plus 0070 plus 060 plus 090 plus 80 plus V plus 0004 plus 00 plus 7 plus 0 plus 6 3 if alpha equals 1/2 plus 0 plus.
Note that an orientation reversing transformation changes the sign of C raised to the ABC power, and hence of the sign of the tensor M raised to the AB power that is constructed from the new C raised to the ABC power by using a fixed epsilon raised to the ABC power. Thus the signatory of M raised to the AB power is determined only up to an overall sign. This is tricky, because a similarity transformation of M raised to the AB power cannot change its signature. Under a parity transformation, both epsilon sub ABC and C sub BC to the A power change sign, and M raised to the AB power is unchanged. The arbitrariness in the signature of M raised to the AB power arises from the arbitrariness in the choice of epsilon sub ABC. A final subtlety in the classification arises from the fact that classes of equivalent tensors C sub BC to the A power correspond to classes of equivalent pairs, A to the A power, M raised to the AB power. One cannot make independent similarity transformations of A to the A power and M raised to the AB power. When A to the A power equals 0, or M raised to the AB power equals 0, we are done. When A to the A power is not equal to 0, and m raised to the ab power is not equal to 0, rank m is 1 or 2. For rank 1, there turns out to be nothing new. For m of rank 2, type 7 and 6 above, however, one can construct an invariant scalar, alpha.
See equation 2-115. Or, equivalently, expressing m and a in terms of c sub bc to the a power. See equation 2-116. There are, then, two continuous families of Lie groups parameterized by a, with a to the a power is not equal to 0, rank m equals 2, signature plus plus and plus. The 3 metric of a homogeneous spacetime has constant components with respect to the group invariant basis, omega to the I power. That is, h sub ab equals h sub ij of omega sub a to the I power omega sub b to the j power, with h sub ij constant. Because the metric is invariant under the action of the group, so are the Riemann and Ricci tensors. Their components can depend only on h sub ij and on the structure constant c sub ijk of the group. In fact, because derivatives of the connection coefficients vanish, the tensors must be quadratic in c sub jk to the I power with the metric entering only to raise or lower indices. The computation of the Ricci tensor is as follows. See equation 2-117. See equation 2-118. See equation 2-119.